Another type of nucleophile can contain sulfur. And thiol group reacts reversible with aldehydes and ketones to form a thiohemiacetal and thioacetal. And the reaction mechanism is the same as we just saw for the formation of an acetal. Similar to alcohols, thiols are relatively weak nucleophiles, and hence an acid catalyst is usually used in order to increase the rate of the reaction. Here you can see the overall reaction mechanism. So we start with either a ketone or an aldehyde with two equivalents of thiol, again with the help of an acid catalyst. Then we form this thioacetal and water. And thioacetals are important compounds for organic synthesis, as they can be reduced by Raney nickel and hydrogen in the so-called Mutzingo reduction. Hereby, both carbon-sulfur bonds replaced by carbon-hydrogen bonds. It means the reaction can be used in order to convert an aldehyde or ketone into an alkane. After the reaction of aldehydes and ketones with oxygen and sulfur nucleophiles, we now continue with nitrogen nucleophiles. And first of all, we will start with primary amines. Primary amines add to the carbonyl group to form an imine. And this reaction takes place in two parts. In the first part, the amine adds to the carbonyl group, and after a proton transfer from the nitrogen to the oxygen, we end up with a hemiaminal. Then in the second part, hemiaminal is protonated by the acid catalyst, and then water is released in order to form an iminium ion, followed by a deprotonation to form the imine. Hence, this reaction can also be described as addition-elimination reaction. So if we have a closer look on the reaction mechanism, we can see that in the very first step, the lone pair of electrons of the nitrogen will attack the partially positively charged carbon in the carbonyl group. Then we end up with an intermediate that contains both a positive and a negative charge. Then we have a proton transfer from the nitrogen towards the oxygen, and we end up with the hemiaminal. And in the second part, we start with the protonation of the hydroxide group of the hemiaminal. Then this intermediate releases water, and an iminium ion is generated. In the final step, the proton from this iminium ion is released, and hereby the acid catalyst is regenerated, and we form our product, the imine. And again, all steps are reversible. And to force the equilibrium to the side of the imine, a drying agent is usually added. Amines are relatively strong nucleophiles, and they add to the carbonyl group to form a hemiaminal without the presence of an acid catalyst. However, an acid catalyst is required to convert the hemiaminal into the imine. And as you can see here, the fastest formation rate of the imine can be achieved if the pH value is 4.5. Conversely, if the pH value is lower, the primary amine gets protonated, and the protonated amine cannot act as nucleophile, which decreases the formation rate of the imine. Conversely, if the pH value is higher than 4.5, there is not enough acid to protonate the hemiaminal, and the formation rate of the imine decreases as well. In contrast to primary amines, where imines are formed, the addition of a secondary amine to aldehydes and ketones yields enamines. And the reaction mechanism is very similar to that of a primary amine, except for the last deprotonation step of the iminium ion. Let's have a look on the reaction mechanism. We can see here that again we start with the attack of the electrons of the lone pair of nitrogen to the partially positively charged carbon of the carbonyl group. Then we form an intermediate which contains both a positive and a negative charge. Then a proton transfer from nitrogen to oxygen is conducted, and we end up with a hemiaminal. In the second part, we start with the protonation of the hydroxide group of the hemiaminal. Then we form another positively charged intermediate, which releases water in order to form the iminium ion. And now we can see that it is not possible to form an imine based on a proton elimination because there is no nitrogen-hydrogen bond. However, in order to form a stable neutral molecule, the iminium ion loses a proton of a carbon in alpha position, and hereby a new carbon-carbon double bond with a nitrogen R2 substituent is formed. This molecule is called enamine. You can see here the newly formed carbon-carbon double bond, and next to it is nitrogen R2 group. Furthermore, our acid catalyst is regenerated. Besides with amines, aldehydes and ketones react also with other nitrogen nucleophiles. And this is depicted on this slide. For example, the reaction of a ketone or aldehyde with hydroxylamine, again with an acid catalyst, yields oxime and water. Conversely, the reaction of an aldehyde or ketone with hydrazine, also with an acid catalyst, yields hydrazone and water. Today, we had a look on a multitude of different nucleophilic addition reactions of aldehydes and ketones with various nucleophiles. And here is an overview about the different nucleophiles and the resulting products. We started with the nucleophilic addition reactions with oxygen nucleophiles. And we learned that the addition of water yields hydrates, which are also called diols. Moreover, we learned that the addition of one equivalent of alcohol yields the so-called hemiacetals, whereas the addition of two equivalents of alcohol nucleophiles yields acetals. Then we also had a look on the addition of sulfur nucleophiles, and we learned that the addition of two equivalents of thiols yields thioacetals. Finally, we also had a look on the addition of nitrogen nucleophiles. And the addition of a primary amine to an aldehyde or ketone yields an imine, whereas the addition of a secondary amine yields an enamine. Moreover, we learned that the addition of hydroxylamine yields oximes, and the addition of hydrazine forms hydrazones. So, to sum it up, we learned that aldehydes and ketones react not only with oxygen nucleophiles, but also with sulfur and nitrogen nucleophiles in so-called nucleophilic addition reactions. And correlated to this lecture, you can do the worked example 23.3 and the end of chapter questions exercise 1D, as well as exercise 2A and B, and exercise 4A, B, C, and E. Moreover, in preparation for next lecture, please read already chapter 23.3 and 23.4, which can be found on page 1082 until 1094.